Hi. Good morning, good afternoon, everyone. Welcome to this session, an overview of polymorphic table functions. So this is a completely new feature that we have added to database 18C, and we can get to the next slide. The primary focus of this is 18C, which is available for download now. So it's been available in the cloud for quite some time. It's been available via Live SQL for quite some time, and of course now it's available for on-premise installation. So you can go to OTN and download 18C now. I may stray into some of the 19C features. So hence, although this is primarily 18C, I've put a safe harbor statement up just to cover myself. To introduce myself, my name is Keith Laker. I'm the product manager for Analytics SQL, and part of my remit is to cover polymorphic table functions. So you've got details of my blog there, my Twitter handle, and if you've got any questions, then feel free to email me as well. So the session agenda for today, I think we've got about an hour to cover this. So this is a session that I did at Open World last year. I'm going to do another one this year, slightly different approach to polymorphic tables. But what I want to do is to give you some sort of a quick potted history. If you're not familiar with table functions, been in the database for a while, so I just want to quickly go back over some of that content just to sort of set the scene, and then we can move into what is a polymorphic table function, why do we need them. There's some key concepts and interfaces to expose to you for you to understand, and then we'll look at a very simple use case for building a PTF, polymorphic table function, and how to use it, and then we'll do a quick wrap up. Okay. Potted history, table functions. So we've had table functions in the database for quite a long period of time. Essentially, they allow you to interact with a data set in a similar way as if it was a table. You can put the table function itself within the from clause, and then effectively we get a row of outputs, and you can then process that output using your own code, and then push that data, that result set, back out to the user. The function itself can be parallelized, although that does take special programming. You have to get into a fairly deep level of understanding of how the table function is going to operate, and when, where, and how your results that are coming back can be parallelized. You can pull data back in a stream so that you can process it without having to stage the data into a temporary table or anything like that. So you can effectively pull data in as it's generated. We have this concept of pipeline, which is typically used as a method within an ETL process, again for sort of pipelining, for generating without staging, just passing through the result sets as they become available. And most of this is sort of directed at application developers who are looking to extend SQL processing to add their own functionality, or DBAs as well, trying to improve processing, trying to internalize processing, and effectively trying to create black box functions to make it easier for end users to consume business specific functionality. So it first appeared in 8i. I mean, it's been around for a long time. And the idea was that we were giving you the ability to create your own custom algorithms and embed those within an object, a table, that could then be reused by non-developers, non-DBAs, in a very simple way. And you basically had three types. So you had a non-pipelined version where we had to build the whole result set, and then we would return the results to you. So everything had to be in place, all your formulas, your processing had to have occurred. We had to have the whole result set available, and then we would push it back to you. Pipelined allowed us to return rows as soon as they were processed. So the pipeline feature gets rid of this need to take a data set and put it into, say, a temporary table for additional processing in the next step. Obviously, the non-pipeline version requires space, it requires memory, it requires possibly temporary storage. So there's lots of implications of creating non-pipeline functions, and a lot of those disappear if you switch to using pipelined. If you want to take it to the next level, you can have complete control over everything via the Oracle data cartridge interface. But now we're getting down into a very, very low level of processing, and you have to have a fairly intimate knowledge of how we internally within Oracle process data, and therefore how you can best surface those results to make use of optimizer features and so on. So you might have, for example, the example that we have in the documentation. We have a table function called getBooks. We pass in a category, a table, and we'll produce a result set from that. And with 12c, we actually removed the need to prefix the table function itself with the keyword table. So you could actually drop that. So now it would be from catalogs, get books, etc. So you wouldn't actually have to prefix it with the table. Although that can be quite useful in terms of identifying to the next person who's coming along, who may have to debug your code, that get books is not a table, it's a table function. So you can produce a table function. It will return you a set of rows. It can be used in the from clause. In effect, it looks and feels very much like a table. Now, some limitations. The row types are determined and fixed at design time. So as you write your code, you have to, in effect, determine the types of rows and columns that you're going to return. Which means that essentially each table function is hard-coded for its inputs. So you can't, in one way, take one particular format and in another way pass in another table and it returns something different. The types of inputs that you push in are preset and then determine the outputs. They can be, don't necessarily have to be, but where you start to try and black box quite complicated business rules, it can get quite complicated to design, especially where you get into parallel execution. And there are a lot of table function examples out there, and some of them look fairly straightforward, and some of the parallel execution ones look fairly straightforward. I have to say, having done a quick search and gone through a lot of blog posts that are out there, a lot of the parallel execution ones are actually incorrect. And one of the difficulties with trying to manage the parallel execution state is trying to ensure that you get deterministic results. And that can be very complicated where we start getting into the data cartridge interface, where you can start to branch out into managing parallel execution states. it's very difficult to fully understand what's going on and be able to ensure that you get deterministic results. So table functions, absolutely fantastic. They've opened up a whole new area for your own unique processing to your specific business application. But there are some complications, there's some gotchas, particularly when you get to parallel execution. Hence, what we're trying to do with polymorphic tables is we're trying to make this whole process simpler for you. And we want it to be a lot more flexible in terms of being able to not be typed or cast against a specific table. We want you to be able to pass in any table or a table with data types that conform to the data types that you wish to return. And therefore, the polymorphic table, as it polymorphic states, should be able to cope with lots of different types of tables being input. So the row type itself can actually be determined by the types of parameters that you push into the polymorphic table function. So this is really useful if you've got applications where you've got sort of generic extensions. You're not really sure what type of table you want to input, or there are lots of different types of tables, but you want to apply a common logic to those input tables, and we'll look at something in a minute. Polymorphic tables will give you a much simpler framework for embedding that business logic inside a table object. So let's sort of dig down into a little bit more detail. So polymorphic tables effectively encapsulates your user-defined functions, and in exactly the same way as table functions, you can reuse them within the from clause. Because they're polymorphic, what we're providing you is a lot more flexibility in terms of processing any table. So the row types themselves are not declared at definition time. The results that came out, they're sort of declared at runtime. What this allows you to do is, in effect, have dynamic SQL. So you can now encapsulate, in effect, create a black box around your business rule and simply pass tables in and have a result set come out, which would be determined in terms of its outputs at runtime. So for example, you might have a credit risk model. You might pass in customers to determine their credit risk, and that customer table might have a certain structure. You could pass in suppliers, a supplier table, which may have a completely different structure, to that black box function and have it return a result in terms of the credit risk associated with either suppliers or customers and so on. So we're trying to reduce the amount of code that you need to write, and to do that we've added some new APIs. If you're already used to the data cartridge interface for doing that, you will be familiar, or the new APIs that we've added will be fairly familiar to you. The idea is that you really don't want to understand, or you shouldn't need to understand, how a table is processed to be able to leverage certain features, and the most obvious one really being parallel execution. What you want to be able to do is create a table object yourself that encapsulates your business rules. And as far as Oracle's execution engine is concerned, this is a standard table that it can process in a standard way, as if it was a normal rows and columns table. that you had defined with create table statement. That was not necessarily true with the data cartridge interface or with standard table functions. A lot of the database processing got switched off, and it wasn't possible to inherit certain features, certain optimizations that we'd made because you were using a table function. As far as you're concerned, if we take parallel execution as an example, if you're a developer or a DBA writing a polymorphic table function, you can just assume that everything is going to be running serial execution. You don't have to think about at which stage can I do this type of processing, and then when all of my parallel execution slaves come back together and we start aggregating results, what can I do at that point, and therefore how do I split out the processing between those different stages? All of that's encapsulated. It's hidden inside the actual way we handle the PTF now. So from your perspective, you can assume serial execution. If it's available, we will run that in parallel for you. So this is an evolution of the standard 8i table functions, the data cartridge interface, a simplification, but it's a lot more powerful. If you think about this in sort of three different ways, you've got the PTF, the polymorphic table function author. That is the person who is going to, if you like, define how the polymorphic table function is going to process inputs and what its outputs are going to be. So this is the person who's going to write the polymorphic table function. The database in itself is the orchestrator, the conductor, responsible for the compilation, execution, and state management. So a lot of the state management, etc., was in table function world, in data cartridge particularly. You were responsible for trying to understand state management, particularly around parallel execution. And the query author is going to be the report builder, who is simply going to take your polymorphic table function and provide the inputs to it, and then consume the outputs as part of their report generating process. So there's sort of three key players in there. First person writes it, second person is going to use it in their report, so they need to know what the inputs are, how to pass those inputs in, and then the database is going to be responsible for the execution, the management of running that polymorphic table function for you. So this is, just to be clear about where this has come from, this is part of the ANSI 2016 standard. So it's not unique to Oracle, but as part of the ANSI, ongoing ANSI process compliance that we have, this is part of the ANSI 2016 standard, so it's part of database 18C. What we're doing here is, as I said, hiding the implementation of the algorithm from the report consumer. So as a SQL report developer, if you wanted to do a credit risk table, get a credit risk result, you would, as a developer, just consume that table as part of the from clause. The resulting row set that comes back, typically as a developer, you're going to return a table, as it shows here on the left, taking a standard data set and then returning information about the credit risk for each individual. But it could come back as JSON, it could come back as XML. It depends on you as the developer of that PTF, what it is that you want to return. You can make changes to the input data. So as the data comes in, you can add columns, you can add rows, you can remove columns, and you can remove rows from the output. So it's a very flexible way of generating a row set within the database engine. So if we take, say, a credit risk model, you might do a select statement, pull out the columns that you're interested in from, and then your credit risk table function, the polymorphic table functions, credit risk, and then the inputs are customers table, and then within that customers table, the key columns are date of birth, whatever their zip code is, and whether they've defaulted on a loan before. And then from that table Scott.customers, we're going to add 2 new columns, which are credit score and risk level. As the results are returned, we're going to apply a filter. So we're going to put a predicate on for the risk level. We're only interested in those high customers, and we're going to do a group by. So you can see it looks and feels very much like a standard table object. In this case, we're passing in Scott.customers, but we could pass in, say, Scott.emp, and we might say the columns that are going to determine whether I'm a credit risk or not maybe are my start date, my hire date, and say my commission. This is the advantage of polymorphic tables. It's no longer a credit risk model tied to Scott.customers. We can pass in any table, we can pass in any columns, and we will get the output columns of credit score and risk level. So, quick summary of polymorphic tables. Firstly, most important thing to remember, we can accept any table. So when you're writing a polymorphic table function, you are not binding it to a specific table. The computations that you put inside the polymorphic table function itself allow you to create a black box solution for your report developers, your report consumers. So you're encapsulating your business logic inside the PTF, which makes the whole essence of writing reports a lot simpler. The output that you produce from that, we can add columns, or we can produce less columns or fewer columns. We can add rows to the result set, or we can produce fewer rows. So if you think about this type of model, you can see things like the window functions that we had and aggregation operations that we have use a similar approach to polymorphic table functions in terms of the way that they produce data, adding columns and processing and parsing data. So let's look at some of the key concepts and interfaces. We'll describe what it should do. The question now is, how exactly do we go about doing that? And we essentially have two types of polymorphic table functions. There's non-leaf PTFs, which are subdivided into row and table semantics, and we have a leaf PTF, which at this point probably is not going to mean anything to anyone. So essentially, for non-leaf PTFs, we input a single table. At this point, having input a single table, we can either be row or table semantic. If you want to add new columns, and you can do that by just looking at a single row, and we'll look at an example of this in a minute. So if I've got, let's say I have a very, very simple PTF. I've got my employee table, and all I want to do is duplicate their department. So in effect, I just want to echo a column, current column, department, and I'm going to duplicate it and just put the department number followed by the department name. That would be a row semantic one. As each row comes in, I can just determine the value of the new column by looking at a single row. Where you need to traverse a number of rows, and this is sort of like a window function type operation, the new column is some combination of the current row plus other rows that have been processed. So you might be doing, for example, a running total. Now I can't determine the total by just looking at the current row. I need to step back over previous rows. So a table semantic, it's going to operate on an entire table or a partition. So we have partition concepts here in a similar way with the window function using partition by. You can partition a table function, a table semantic PTF. And the row semantic one, for each row coming in, you will get a single row. So input row, output row. Very straightforward. The table semantics, as I say, you can think about that for the way we use it today, in effect, is for doing analytic functions, aggregations, windowing functions, etc. Those are implementing under the covers similar operations to a table semantic PTF. Now, the advantage of taking your existing table functions and moving them to the PTF model is that we've got some optimizations built in here. So what we try and in essence do is minimize data movement. So if I pass a table in to a PTF, I can identify the columns of interest within that full table that require the PTF to process them, and the other columns can be ignored. So we're optimizing the execution space that we need by only focusing on specific columns within a table rather than having to traverse the whole table. We can get predicates, partitions, projections, etc. into the underlying table. Those are pushed down into it, so we can do additional filtering where that's semantically possible. You can do, or there's optimizations that we've put in where we need bulk transfers into and out of PTFs, and the parallelism is managed by us and will be driven by the type of PTF that you create and whether you're using partitioning. So this in effect is trying to say to you, create a table function, a polymorphic table function, and transparently there's optimizations that we're now going to do to ensure that your PTF runs as efficiently as possible. So there's nothing that, unlike say data cartridge interface or some of the other types of table functions that we were using pre-18C, there's no need for you to sort of get involved in the execution space in trying to understand and optimize your code based on how you think it may or may not get executed. The idea is to sort of get you away from that. So let's look at some of the interfaces. If you've used the data cartridge interface, this is going to look fairly familiar to you. So the first part that we need to build is called the describe phase, and this is required, this is mandatory. So you have to give us some guidance on the shape of the output that you are going to build as part of your PTF. That's in effect the only mandatory part. So all you really need to do is give us the definition of the output table shape. The open is the next part. It's optional. You obviously don't have to do any processing at that point, but this is just sort of the setup space before you get to the actual processing part. The workhorse where all of your business logic is going to be applied is in the fetch rows section. So this is where you're going to start working on the subset of columns and rows that you've got. You're going to be generating the new columns and the new rows, etc., for your output. And then finally, we have to clean up. So we have the close element, which is going to go through and, as it says, tear down all of the processing space that we've consumed, tidy everything up, and effectively leave the environment as it was when we first started processing the table function. So what's the purpose of describe? What do we do in that? So you typically in here are going to give information such as, okay, I'm going to create a new column, and we'll see how we do that. There's an example in a minute. So we have this idea of, as I said, we have optimizations that allow us to look at a data, the table being passed in, and determine if we need to read that column because it's going to be used during execution, or whether we can just pass it through. And in effect, we don't need to do anything with it. Column's going to be untouched. In effect, it's just part of the general output. There's no need to do any processing on that. By default, we're going to assume, if you give us a table, that all columns are passed through. Hence, part of the describe process is to determine, as a developer, which columns need to be marked as read columns so that they are then exposed, ready for processing. The fetch rows is for, say, a non-leaf PTF, the stream of rows divided into, in effect, arbitrary chunks or row sets. So this is, in effect, now we're into building in a similar way an execution environment to how we would process a table. So a table is processed through row sets. Your polymorphic table now becomes a row set, and we'll consume those rows from the input stream, i.e. the table that you're passing in, and we'll have what's called an active row set. And then we need to produce the new columns that we want to add, and if we want to add any rows as well. So a good example of adding rows is the cube roll-up functionality in the group by. Now that's where you start to add new rows. That's a good example of sort of an active polymorphic table type operation of adding new rows into a result set. You may end up seeing that the fetched rows gets executed multiple times. As I say, as far as you're concerned, the way the polymorphic table function is processed, you need to think about that only in a serial execution way. How the fetch rows is going to be executed is internalized, so you don't need to worry about that. And if you're looking to understand, okay, when have I finally got to the last row set, the last row in my system, it will have an Endoffile flag, and that's available for you to query. So you can parallelize a PTF, but there are some twists here. Oops, I've marked them both as one. Should be 1 and 2 there. So if you're doing a table semantic PTF where we need to process the whole table or a group of rows before we can determine the output on another row, that parallelization operation will be based on the partition by key. So all rows within a given partition must have the same slave. So that allows us to, for example, ensure, let's say we want to do a running total, that we have the correct rows in place to be able to issue a running total, if that's what your PTF was going to return. You can't do interpartition parallelism. So you can't sort of jump across partitions. And also you can't further subdivide your parallelization. But again, as I say, the key thing is the ability to internalize all of this operation. So if you wanted to do a table semantic partition by operation, you can say, for example, if row num is by PTF, you can pass in emp and tell us, okay, partition by department number and order by hire date. So now we're going to take that PTF and we will break it up by department number and sort the data within that automatically by hire date and process it accordingly, and then filtering out all of those where the department number is not equal to 20. So it kind of follows similar rules to a lot of things that we have. We've got similar concepts to the data cartridge interface. We've got similar concepts to analytic functions. You also need to be aware of this additional package, which is the way we managed to create flexible PTFs by not binding your PTF to a specific table or a specific row type. And we do that by using metadata. So rather than specifically referencing a table and a column within that table and that column's row type, you are going to now use a package which interrogates the table that you're passing in, or the column that you're passing in, or the row set that you're passing in, and discovers the necessary data types to make that return that data as part of the return process for that table function. So there's a new package in 18C called DBMS_TF, and it provides ways, internalizes the interrogation of basic metadata about the information that you're passing in to allow the PTF to be completely flexible. So this in effect it's just a module. It's a metadata module. It's got effectively support routines that you're going to need to implement any PTF that you need. So when you provide an input table, the descriptor phase, the describe phase of your PTF function is going to need to understand information about the table that you've just passed in, because we're not fixing it to, as in the credit risk one, customers or employees or suppliers. It could be any of those tables. Therefore, we need to interrogate metadata. So we have table_T is the descriptor object that's going to get me information about the input table. If we want to add new columns, there's a columns new_T, which allows me to insert new columns into that PTF, and hence the return data set, row set that we produce. Now this can, because we're creating a black box here, you effectively give us the table, you give us the columns that you want to pass in to the business logic, and a new table with either additional columns and or additional rows is automatically returned to you. Trying to understand how that PTF is processing can be tricky. So one of the additional features of this DBMS table function package is to provide a trace console that allows you to get information about how your PTF is functioning. So let's look at a very, very simple example. So the first thing I'm going to do is I'm going to take an input table, and I want to return all of the columns from the input table, but I want to duplicate 2 of those columns. And in the duplication process, I want to add some additional text. So for this idea, I'm going to take whatever the column is, and I'm going to, on the input data, I'm going to prefix the word echo and then output that row. So this is a row semantic polymorphic table, because for each row I can, in effect, as the input row comes in, determine exactly what needs to be duplicated. So this is a row semantic PTF. So the table operator is no longer required. So you can see here I've got select star from, I'm going to call my polymorphic table function echo. My table going in is the department table from Scott schema, and the columns I want to duplicate are the department name and the location. So if I pass that in, select star from echo, department, column names, I'm going to get department, dname, location, and I'm going to get back echo underscore dname, echo underscore lock, and corresponding values from these rows. So you can see here the select star function still works. In database optimizations, as we see later on, will also work. But what if I want to join 2 tables? Let's say I want to do this on the EMP table, but I want the department name. So now I need to join on EMP and DEPT. How can I do that? Can I pass in EMP and DEPT here to make sure that dname and location still comes back? That's kind of tricky. At the moment, no. We have to pass a single table name in. If you want to pass in multiple tables, then in effect, what you have to do is create a with clause to do all of the pre-processing that you want to do, any joins, etc. And then you can pass that details, oops, scrolled in, pass that information into your polymorphic table function. So there's a, if you like, a slight twist to this, where you're processing for the input data is a little more complicated than just saying, here's my table and take these 2 columns. All you need to do sort of more sophisticated processing is just build a simple with clause around that. So as you can see here, what I want to be able to do is enter in a similar way clauses that we did before. So I'm just going to copy them out. But again here, I'm using the same table, echo, but now you can see I'm passing in EMP. And I'm passing in 2 different column names. This time it's ename and job. And I'm applying a filter where department number is 20. And I still get the same result. So it takes my input columns, ename and job, and it now echoes them out. So here's the benefit of PTFs. I can provide any input now, and I can provide the output columns that I want the processing, or the input columns that I want the processing on, and I will get my corresponding data set back. So I can use the same polymorphic table function echo on the DEPT table, on the EMP table, whatever it is. So how would, just looking at that very simple package called echo, how would I define that? So I have to create a new package. Remember I said there were 4 procedures: describe, open, fetch, close. I need to provide inputs on the way that the data is going to be processed and the inputs that I'm expecting. So I'm going to add new columns, but at this stage I don't know what the data type of those columns are. So I use my metadata package, DBMSTF, to in effect type the columns on the basis of the fact that I'm going to add new columns, and I'll determine those at runtime as to how those the data type for those columns. Then I've got additional arguments, which are the table that I'm going to pass in, whether it's department or employees. That also needs to go out as well, because I'm going to return the employee data or the department data. And I've got columns that are coming in. And again, I don't know what the column types are. So I'm going to get the column types that are going to be provided at runtime. So this DBMSTF package effectively allows us to accept any input as a table, any columns as the inputs to the processing, and then in this case output replications of the columns to create new columns. So once I've got that, I can create and replace my function echo. I've got tab as my input and cols as my inputs. It's a pipelined row polymorphic table. So as I said, it's a row-based polymorphic table. As each row comes in, I can immediately determine what the values are for the new column. So it's row semantic PTF, and I've set that up. So I've got my new package, which is my new function, which is going to be called echo. I now need to create the describe functions and the processing that's going to be associated with it. So the first part of the describe is to get the inputs and explain the outputs. So we get that from the first part. So what I'm going to do is I'm going to straight away say, okay, I'm actually in the describe phase. So my DBMS trace output is just going to say, okay, we're in the describe phase. So I know which part, when I call this, which part of the package I am in. Then I need to build out the new columns. So I need to add some new columns because I'm going to echo the columns that have been passed in. So again, I'm now going to go into a loop for the columns that have been passed in. And then just so as I know exactly what's coming in, what's going to be going on, I'm going to put some output information that say, okay, I'm reading this column. And you'll see this in a minute. And then I'm going to go through, I'm going to mark the column as being read. I'm going to give the column name echo underscore whatever the current column is, and that's going to be assigned to the new column. I'm then going to update the fact that I've read that that column value. So if I'm going to add two columns, I'm going to go through twice. So I update my column counter, and we'll do some quick error checking. Maybe somebody gives me a wrong column name. I just need to make sure that that's catered for, or maybe I try and create echo underscore and that already exists. So I may have duplicate column names. So what comes out, when we execute the PTF, what we'll get is describe function. Okay, the read column is ename, and the second read column is job. So if we just quickly go back, so you can see here, I'm going to echo, I'm going to take in emp, columns I'm going to pass in are ename and job. So when I run the describe, I'm going to get the fact that I need to process ename and job. So that's the, if you like, the background output that I'm going to generate. So the next one is the open procedure, and I'm just going to get some environmental information. And again, I'm going to use trace to say, okay, I'm in open mode. So I'm into the open function. I'm going to get the column count, pick up some information and just push it out. That's all I'm going to do. So it's going to say I've got 2 columns to process and I now need to add 2 additional columns. That's in effect all the open's going to do for me. It's not going to do anything else, doesn't need to do any processing. That's it. The bulk of the work is all done in fetch rows. So this is where we're going to pull out and process our data. So I need to know how many columns have I got to process. Well, I know that it's going to be 2. Okay, so what do we need to do? First thing we're going to do is quickly push out the trace information. Okay, I'm now in fetch rows. I'm in fetch rows mode. Okay, which column am I processing? So I'm going to get the column here, and then I need to know from a tracing perspective, okay, here's the column and whatever the column is. So I'm going to get column 1 equals whatever it equals. I'm going to echo this. So my column name, my column value that's going to go into column 1 is going to be echo dash, whatever the column is. And that's effectively it. So all I've got to do is take whatever the column is, the 2 columns that I've processed, that I passed in, ename and location, I think, and return the value with echo attached to it. So if I process that now, it's going to say, okay, I'm on column 1. First value is Smith. Column 1, the second row is Jones. Column 1, the third row is Scott. Column 1, the 4th value is Adams. Column 1, 5th value is Ford. So what I should see is echo Smith, echo Jones, echo Scott, echo Adams, echo Ford. Then I can go on to column 2 now, and the first value is clerk, so Smith is a clerk, and we'll say echo clerk, and so on. So we'll then start processing column 2, and then we can close. So having echoed those values, I'm then done. A close procedure, we can just say, okay, we're done. That's it. So in effect, you just get a value or a table object that you can play with, and you can inherit all the features that were built into the optimizer as if you were running a natural, stored table. So in this case, we've got polymorphic table, row semantic called echo, inputs are emp, columns that I'm going to pass in ename and job, and you can see here I've got echo Smith, echo Jones, echo clerk, echo manager, and so on and so forth. Now, if you then start looking at the explain plan for this, you will see that you can see the fact that we're actually going to use a polymorphic table function. So you will see in your explain plan the name of the function and the fact that you've got a PTF in operation, which is quite useful. Let's say you enable this for parallel execution and execute it in parallel. Is there anything, do I need to change anything in my table function now? If you were using data cartridge interface, you'd now have to go back and make sure that the code that you were running, you were getting deterministic results, or you might have to move some coding to the end of your processing once the parallelization has occurred, and you can bring together the results. You don't have to go to that level of understanding now. You can take the same function, echo, and we can do the echo without having to understand, okay, what happens if we have 2 parallel execution slaves running. What happens now? You're just going to inherit the ability to parallelize your operation without having to get into the internals. One of the features that we added in 12.2 for improving reusability is in-memory cursor duration temp tables. So what we will do is, if we're going to reuse results across a number of different operations, we will use an in-memory table to materialize those results to make access for reusability much, much faster. So as I said, if you want to do quite sophisticated processing on your input table, what you need to do is use a with clause to, in effect, encapsulate that complex processing, and then you can pass the results in to your polymorphic table function. Hence, what you want to be able to do is pick up the fact that you have this reusable component and you'd like to have that established as a polymorphic table function, but reuse it with cursor duration temp tables. It will happen automatically for you. There's no additional changes that you need to make to your PTF to inherit the ability to leverage cursor duration in memory temp tables. It just happens automatically. Now, a lot of this wasn't possible if you were using table functions or if you were using the data cartridge interface. But now, because the polymorphic table function is in its essence a row set object, and we're able to use result caches or push that data into a result cache to make it more useful and optimize the processing. So as I said, you can't do nesting either. If you want to do typical type nesting, etc. operations, like, okay, I want to change the way that a return type is managed. For example, I want to change the case, do some processing, and then do an initialization capital on a particular column. Can I do that? So I've got a polymorphic table called change case. I've got a polymorphic table called get call. How would that work? It's not. You're going to have to do it in 2 bytes. It's not a huge issue, but it's just something to be aware of, and it's relatively simple because you just use the with clause. You can do different types of PTF, so we can just do a describe only PTF, which is kind of weird, but the capability's there. I'll let you walk through that example of when you'd want to do that. But essentially, this is a very, very, very powerful new feature. There are lots of examples on LiveSQL. So if you want to look at livesql.oracle.com, you'll see already that people have started to post polymorphic table function examples. They're much, much easier to design and build, purely and simply because we're encapsulating the processing for the execution of that polymorphic table function. You no longer have to understand how Oracle is going to process your data set to make your code deterministic. And rather than writing a table function for each type of table that you need to pass in, you now have this reusability, hence what's called polymorphic table functions. So it's much, much easier now. It's very straightforward, taking it up at a significant level, particularly over things like data cartridge. So that's about it. I will make the slides available. As I say, if you have any questions, then let me know. There are examples already up on LiveSQL, and hopefully the slides will give you some good use cases. I'm going to be doing another session open world this year, more code examples. I'll pass the slides on as soon as I finish the examples. So if you follow my Twitter feed or look at my blog, you'll see after open world there's a bigger deep dive into polymorphic table functions that hopefully you'll find useful. But this should get you started, and I'm sure there'll be lots of things that you can do with PTFs. So enjoy them and be successful. Thank you very much.